Hey guys, so for this module we'll be looking at an introduction to numerical techniques. So the first thing we're going to cover is how to solve system of linear equations. So no doubt you've seen system of linear equations before in your high school courses in Algebra 1, 2, whichever courses you took. And boiling down, all they are, so if you have a system of n linear equations and they have n unknown variables, you can call them x1, x2, whatever, then usually they have this sort of setup. So you have some sort of constant times the first variable plus second constant times the second variable, so on and so forth, and that's equal to some constant value. And you have as many of these equations as you have variables. And then usually if you're doing this in high school and by hand, you would use an elimination technique or maybe substitution or other such techniques, but we're going to be using Matlab to do this, and Matlab is good at matrices. So what we can do is, for example, let's take this smaller system of three equations. So you have this 3x plus 2y minus z equals 10, negative x plus 3y plus 2z equals 5, and x plus x minus y minus z equals negative 1. If we turn this into a matrix formalization, here's what we can end up. So we move all the constants into one matrix, we call that A. So there's 3, negative 1, 1, 2, 3, negative 1 over here, and then the last one, negative 1, 2, negative 1 for the z. They all get made into one matrix. Then we have this other matrix right here, which is really just a column vector representing the x, y, and z variable. And then you just have all the constants that were on the right side as just constants. We call that the B matrix, or it's the B vector really. And if you notice, they're all in order. So it's x, y, and z, x, y, and z, x, y, and z, x, y, z, x, y, z. You need it to be in this order in order for the matrix math to work out. So now that it's in this matrix form, you can solve this in Matlab using a couple of techniques, but we'll go over two methods. One is using the inverse of a matrix. So if you remember back in linear algebra, if you're taking it, or even in the old matrices and vectors module I taught, if you have a matrix like this, so A times X equals B, you can actually solve for just X by itself. And if this were just an equation, you would divide both sides by A, and that was it. But because this is matrix math, you have to remember that you don't really divide by a matrix, you multiply by its inverse. So what you can do is, you multiply both sides by the inverse of this A matrix. And if you have the inverse of a matrix and you multiply by the original matrix, you create what's called the identity matrix. The identity matrix is the same thing as saying just 1, but it's in matrix form. So you can imagine, multiply this side by A minus 1, multiply this side by A minus 1. The A minus 1 and A here become the identity matrix I, and it just disappears, and you just have X by itself. And over here you have the A minus 1 and B, which is exactly what you have here. So that's one way you can solve it, using the inverse matrix method. The other way is you just directly say, so that's actually the notation for it, but in Matlab, you don't, there's a couple ways to do it, but in Matlab speak, if you want to find the inverse of a matrix, there's a specific function dedicated to it. It's called INV for inverse, and you just pass it the name of the matrix you want to inverse, and that's it. So this x equals inverse A times B becomes x equals inverse A times B, but instead of doing A to negative 1, you just call the function inverse instead. The second method is using what's called left division, which is Gaussian elimination, which you might have also done in high school, depending on who your teacher was. And for that, if you want to solve AX equals B, you just do A/B, and that's it. The actual mechanism by how Gaussian elimination works is not something we're going to cover, but those are just the two different methods. You can either use this inverse of matrix A method or Gaussian elimination. So let's go ahead and do this little quick example, and in Matlab. All right. So let's do a system equation examples. All right. So let's do a clear CLC close all. Create the matrix. So the one that is being used in the example has A equals 3, 2, negative 1. Then it has a negative 1, 3, 2, and then it has a 1, negative 1, and then negative 1 as well. Close that matrix, and let's just check if this works. It works properly. All right. Yep, we got a nice little 3 by 3 matrix. Now don't forget we also have to make our B vector, and this is 10, B, negative 1. And remember, this has to be a column vector. All right, perfect. Alright, so now two methods for it. One is using the inverse method. So we can say x is equal to inverse A times B. And if you run this little section, you get the answers as -2 for x, 5 for b, 5 for y, and -6 for z. There's another method is Gauss elimination, I think I spelled that right, which is x is equal to a/b. And if I run this, you get the exact same values. Now, why would I show you both of these methods if they have the exact same results? Well, for computation reasons that I really don't have time to go over, doing a/b has more, let's say, usability, and it's slightly faster to use than this inverse of a times b method, because this inverse of a times b method requires this matrix a to be square. However, if you use this a/b, Matlab under the hood has algorithms in place to check what the size of both of these matrices are, and it's way more complicated than I have time to explain, but both of these methods lead to the same answers. However, this method right here is a bit slower than this method, and I think I can actually show it to you. So there's a function in Matlab that you can use to test how quick a certain line is. So if you type in tick and then tack, and then let me just do this, and if I run this, you can see this line right here between the tick and the talk took this amount of seconds to compute. And if I do tick and then talk over here, it was faster by maybe, I would say, 3 orders of magnitude faster. So it's more efficient, it can handle more differences in matrix sizes, and doesn't have to be square, and it's just a faster way to do it using Gauss elimination method. But I just wanted to show you guys the differences between them a little, and either one can be used really. So join me in the next video when I'll talk about interpolation. See ya. Hey guys, so now let's talk about interpolation. So if you have a set of XY data that you collected during some experiment, you're not always guaranteed to record all the data points that you want to have recorded. Sometimes it's a hardware issue, sometimes it's a software issue, whatever. So you'll have a limited set of XY data. You can use interpolation to fill in the gaps between the data that you don't have. And there's two general ways you can do it. They're common, and there's more complicated methods available as well, but I'll show you guys how to do linear interpolation and what's called cubic spline interpolation. So here's how linear interpolation works. If you have two data points, say right here and right here, you can connect those with a line using linear interpolation. And then if you want to know what's going on in between, let's say at this x equals 2.5 value, well, this line interpolates between these 2 points, and you assume that the value that this line crosses between these 2 points is a good estimate of what the value is in between. So in this case, at x equals 2.5, it looks like y is about 5, and so that's what your linear interpolation will lead you to suspect. So in Matlab, you can use what's called the interp1 function. So it's a function that where you give it one vector and another vector. So it's xy data, and then you give it a value that you want to interpret. So in this case, you would have given it the xy data points of these two spots, and then asked it for this x new, this 2.5, and it would have spit out about 5 for you. Now what spline interpolation does is it basically almost does the exact same thing, but it's smoother in how it transitions between the points instead of it being a singular line. So let me just show it to you guys right here. So if we move this over here. So edit interp examples. So clear CLC close all. Example 1. So let's make up our data. So it looks like it's 0 to 5. So 0 to 5. And our y's are 15, 10, 9, 6, and 2, 2 and 0. Okay. So if let's just quickly plot this, just see where it is. Alright, so it's a line that goes like this. And if I want to figure out what is going on in, let's say, 2.5, so let's have everything be just circles. So if I want to figure out what is going on in 2.5, you figured it's something close to this value, something close to this value. So it's probably something in between here. So it might be close to maybe 8-ish, maybe. But let's figure this out. So we can just type in interp1, give it the x, give it the y, and then ask it what it is at 2.5. And the answer was 7.5. So the value right here, if you just connect these dots together with a single line, with a single interpolated line, would have been about 7.5 here. And if you want to instead do spline interpolation, we can just do spline. And if I run this part of the code, it gives a slightly different value of 7.8. Now we can have both and ask Matlab to just plot both. So what we can do is have this is X or Y spline. I'm going to copy this, paste it back here, remove this. Y, let's call that linear. And instead of giving only a single value for the Y new, let's have this be a vector. Let's call this X new. Call this X new. And then we can say X new goes from 0.1, spacing of 0.2, and it goes all the way to 4.9. Alright, so now this is the original graph of the data points. And we can do a hold on, and then plot the new stuff. So now we can have a plot of X new versus first the linear. And then we can do a plot of X new and the spline. And we plot all this. So you can see here, maybe I should put legend here. Legend data points for this. Then we have the linear, and then we have the spline. There we go. So you have the data points here. And you can see the linear interpolation, which is in red, just makes a straight line between each of the data points. But the spline does a more smooth transition between the points. Either way, their answers are almost identical to each other. So that's how you can do linear and spline interpolation. In the next video, I'll show you guys how to do curve fitting and regression. Alright guys, so now I'm going to teach you guys about curve fitting and regression. So up till now, what we've been doing is interpolation, which means a function that goes through every single point. So if you remember back into this example we just did, these lines and curves that we fit through here, they go through every single one of our data points. So that's an interpolation. However, you don't necessarily always want that, because sometimes you're recording a bunch of data points and you don't want a function that just hits every single one of those data points perfectly, because maybe there's a bit of noise in your data or some other reason, and you just want sort of a line that generally follows and curves with your data to within a degree as best it can. That is where regression comes in. So what it tries to do is best fit, which means regress, a data set by doing what's called minimization of the sum of squares of the deviations of the function from the data. Now that sounds like a lot, but I'll explain it along the way. So the two types, just like before, are linear and polynomial regression. So linear regression is where if you have a bunch of data points, you try to fit a line between them all such that it doesn't pass through every single point. It's just that it tries to minimize the deviation between where the line is and where your actual data point is. And whatever line has the least amount of this deviation between all the points, that is the best fit line. And if it's a line that has the form of the mx plus b, so a1x plus a0, so this could be like y goes 3x plus 1, for example. So this distance right here, this deviation, we usually call it the residual, the difference between the line itself and the data point. And the least squares fit is how we figure out which one of the hundreds and thousands and infinite number of lines that could possibly fit here is the best line. What you do is you basically take the difference between, well, the residual, which for this line and this point, this point, this point, this point, this point, and this point, add them all together and square them, and that's called the sum of squares, which is residual error, deviation, whatever have you. And that's for a line. Similarly, for a polynomial, instead of trying to fit with a single line, you just try to fit it with a polynomial that has the form of an times x to some power and so on and so forth. So this a is just a constant, and this x could be some sort of higher order polynomials, quadratic if it's second order, cubic if it's third order, and so on and so forth. So if you have only two data points, x0, y0, and x1, y1, you can connect them with a line and you can interpolate between them. And if you have n plus 1 data points, so like 5 data points, and let's say for example, you are guaranteed to find an n-degree polynomial that interpolates between them. So if you have 5 data points, there exists a 5th-degree polynomial that goes through every single one of those data points. But if you have n plus 1 data points, for more than n plus 1, so let's say you had, I don't know, 10 data points, there could be or you have more than 10 data points, let's say for example, you don't necessarily are guaranteed that there exists an n-degree polynomial that can match it for every single data point. In this case, the best thing you can get is a best fit polynomial that minimizes sum squares error. Meaning, if you have, for example, 10 points here, so that'd be 9 polynomial. You aren't guaranteed that a 9-degree polynomial will pass through all of those points perfectly. So here's an example here. So you have these data points here, 6 data points, and you're trying to connect them with a first-degree polynomial or just a line. And you can see this line doesn't go through all the data points. It doesn't go through any of the data points actually. It just follows the general trend of the data. So it's a best fit. It's a linear regression. Likewise, if you have the data points here and you try to do a third-degree polynomial fit, it seems to be a better fit here because it follows the shape of the data a bit more nicely. And this one likely has a lower sum squared error than this. So how do you actually do it in Matlab? There's 2 methods for it. We can use Matlab to easily identify the n-degree polynomial that interpolates a dataset if it's n plus 1 data points, or does it best fit if you have more than n plus 1 data points. 2 methods. The first method is more coding based, so you can use what's called Matlab's polyfit and polyval functions. The second method is built into Matlab's plotting, which is using Matlab's figure menu. So I'm gonna go over both. So if you want to use the first method, which is the functions, the 2 functions you're going to need to know are polyfit and polyval. Polyfit calculates the coefficients of a fitted polynomial for you, and polyval actually takes these coefficients and evaluates it for a given range of x values. So here's how you use polyfit. You give it the x and y vectors that have the data points you want to do regression on. Then you state n, which is the order of your polynomial you want to try, and a is going to be the vector coefficients for your polynomial. So by the vector coefficients, it means it's going to be based off what value of n you picked. It's going to tell you what your n minus 1, a2, a1, a0, and so forth are. And once you know what those coefficients are, you can pass that to polyval and then give it a vector of data points. You can make them a very large vector, a very small vector, and this polyval will evaluate all of these x values that you give it based off the coefficients in A and spit back out to you this y pol, which gives you a vector containing the polynomial values. So let's go ahead and do an example. Alright. So I'm going to make a new file. So edit regression examples. Clear CLC close all. Let's call this example 1. So it's going to be x is equal to 0 to 5, and then y is 15, 10, I think it's the same as before. I think it is actually. So I'm going to go ahead and grab the plotting stuff from here. Alright. So remember how polyfit works? You give it the x data, the y data, and the order of the polynomial you want to fit. So in this case, let's try a third order polynomial. And if I ran just this part of the code, oh, I spelled it wrong. Not polyfit, polyfit. Now if I run this part, you can see here we have the different coefficients for our third order polynomial. So this would be the coefficient for x cubed, x squared, x, and then here's our constant. And if we want to actually use it, we can make our smooth x variable, and let's have that just go from 0, spacing of 0.1 to 5. Have our y pol be polyval. So now we're going to evaluate this smooth x using the polyval function. A.smooth x. Awesome. Alright, and now let's plot both. So plot smooth x and y pol. And so we're going to have our data points, and then third order polynomial fit through it. So if we run our code, you can see here, it doesn't interpolate between any of the points, but it tries to find the line of best fit between them. In this case, for our third order polynomial, here's what it looks like. Alright, now let's try doing the second one. So in this case, it's fit a second order polynomial to data and estimate the sum of squares error for the fit. Alright, so let's try this. And naturally, you could pause the video and try it yourself. or just follow along with me. Either way works. So, example 2. And I believe we use the exact same data set, but just for nicety's sake, I'll copy stuff over. So now, instead of it using a third order polynomial, they want us to use a second order polynomial. So I'll change this to a 2. And if we ran this, here are the coefficients for our second order polynomial. And if we do y poly n, I suppose, and have that be y polyval, a comma, and we try to do it at every one of these points. So remember what the question asks you. It says estimate the sum of squares error for the fit, and if you want to estimate the sum of squares error, you need what the value of your polynomial fit is at each one of the original data points, and then you find their difference and such. So we're going to evaluate our polynomial using its coefficients at each one of the original x values. So if I run this, maybe give myself a little bit more room. Maybe a little bit more room. See if we can squeeze it in. There you go. So here's what the values are according to our polynomial, our second order polynomial fit. And our original value is this y. So if I try to show you guys both, you can see here, original value was 15. Our second order polynomial fit is 14.46. Original value was 10. We got 11.36, and so on and so forth. And if you want to figure out what the sum of squares error is, well, we can say that's SSE. So we want to find out what the difference is between what we have versus the original minus what we have, so y minus y poly n. Then we square it. And remember, because they're both vectors, you want to use the dot notation. And then now we just find the sum of all of this. And we use the sum function for that. So this value is 3.264. A small value, but maybe it could be better. Don't know. We can actually try it out. So how was our third order fit if we tried it? A bit better. A bit better. So that's example 2. Alright, so now we're going to do example 3. So use a polynomial to regress exactly. Oh, so they want us to interpolate the following xy data points. Alright, so let's, and you don't want to do regression, you want to do interpolation now. Alright, so let's try this out. So I'm going to put back the semicolons here. Example 3. And then it looks like x is 1, 2, 4, 5, and 7. And then y is 11, 13, 15, 25, and 40. Awesome. Alright, so first let's take a look at what this data set looks like. And because I'm slightly lazy, I'm just going to copy this, paste this here, run this little section. So it looks like it's sort of increasing with x in a sort of a very non-linear way. Alright, so because it's a non-linear type of fit, interesting. Use polynomial regress exactly. So instead of having us do the what's it called? Using the Matlab functions polyfit, polyval, or going back to interp1 or something like that, or interp spline, let me show you how to use it using the second method I was talking about, which is the using Matlab's trigger menu. So the way you use it is first you have to plot. So if we plot data here, then you go to tools. Oversee here basic fitting, click that. And you now have free control over any type of fitting you want to do over the data set that you have in this window. So if I do a spline interpolation between them, you can see MATLAB automatically does a spline interpolation as best it can. If I try doing a linear fit, MATLAB automatically makes a linear fit. And if I want to know what the equation of that was, I can do show equation. So in this line right here, it's 4.7x plus 3, but clearly this is not the best based off just looks. So we can also do a quadratic fit and see how that works. You can also do a cubic. Let me bring back the equation. You can also do a fourth order polynomial. And if we try to go for more a higher degree polynomial than we have data points for, it says the polynomial is not unique. The degree is greater than the number of data points. So you can't really trust this equation because you have less data points than are needed to actually fit this equation. So let's go back to the fourth order. So this interpolates between every single point, which is what we wanted. And if we have the equation, it looks like this. And how do we know that this is a it's actually going through every single point, well, we can look at the residuals. And you can see here the residuals are really small. Look at this graph. The y-axis is 10 to the negative 12. And if I compare that to the cubic, so you can see now our residuals are much larger. If I compare it to the quadratic or the linear, you can clearly see linear, which is the yellow line, is the worst, and the fourth order one, which is interpolation, is clearly the best, but it goes through every single point, which might not be ideal. Alright, so that was a fun little exercise. Now let's do this one right here. So example 4. Use a second order polynomial to best fit regress the following XY dataset. So looks like we have a new dataset. So let's close this. Actually, I believe it's the same dataset. Yep, it's the exact same dataset. So let me go ahead and bring this back up. Tools, basic fitting, and they want us to do a second order fit, so that's quadratic. Look like this. Let's see the equation. Here it is. So it does a regression, but not interpolation. And the error between them can be seen in if you plot the residuals. And if you do this show norm of the residuals, that's the same thing as showing the sum squares error. And I think that's it. So the equation that Matlab spit out for us is 0.94x squared minus 2.8x plus 13. That is a single equation that gives you the smallest sum squares error for all second order polynomials that could possibly exist based off this dataset. And the more nitty-gritty of how the algorithm works and how you can write your own, I'll leave that for the modeling simulation course for you to learn. But I think that does it for this entire module. So I hope you guys enjoyed that. See you guys in the next one.